All right, folks, it's back in action here. On this page of notes, we are going to start solving exponential equations. Before I get too far, though, I do want to remind you that if you are not one of my students and you are looking for a printout of these notes so you can follow along, there should be a link in the channel description where you can follow that link and just find your way to a Google Drive and download those notes. All right, now, solving our exponential equations are generally going to fall into two categories, as listed here on the top of the page. We will either have an exponential equal to an exponential, or we'll have an exponential equal to a number, okay? Now, in order to solve, starting here at the top, in order to solve, we're going to need to rewrite our equations into one of these forms. Now, they're not always going to fall into these two forms. We're going to look at two exceptions to this throughout this chapter, but these are the two most common ones. When it's an exponential equal to an exponential, the first thing you want to do is make sure that the bases match. And then we're going to set the exponents equal to each other. If it's an exponential equal to a number, meaning you can't get the bases to match, we're going to rewrite the problem as a logarithm, in which case we'll have to do a decimal approximation. So let's take a look at these four scenarios, and then when we get to the bottom of the page, I have one that's just slightly different for us to work with. All right, on our first one here, I can see that I have this 1/5, and I have this 1/25. And with some experience, those should jump out to you, that those can both be written with a base of 5. So I'm going to rewrite the left side as 5 to the negative 1, and then I'm going to multiply my exponents, x plus 7, and the right side's going to be 5 cubed, and its exponent is 3x minus 10, and I'm going to multiply those exponents. Now, if both sides are 5 raised to a power and they're supposed to be equal, then their powers should also match. So I can continue my solving by setting the exponents equal to each other, and I'll have a negative x minus 7 equals 9x minus 30. Move my variable to the right, I'll get a 10x. Move the constant over to the left, I'll get a 23, and x equals 23/10. And since exponential functions have a domain of all real numbers, I don't have to worry about whether this is an extraneous solution. On the next one, it looks pretty complicated, but on this right-hand side, I see that everything is a base of e, so I know that I can combine those. I also know that these two exponents right here should multiply, so it might be helpful if we rewrite that right-hand side first. So we first have an e to the negative x squared, and that's going to equal e to the 2x over e cubed. Now my exponent rules say that if these bases match, I can subtract these exponents. So I'll end up with e to the negative x squared equals e to the 2x minus 3. Now my bases match, so I can set my exponents equal to each other. So I have a negative x squared equal to a 2x minus 3. Now it's a quadratic, so I'm going to move everything to one side. So I'm going to have 0 equals x squared plus 2x minus 3. Certainly a possibility would exist that this would be a quadratic that I'd need to do the quadratic formula on or complete the square, but this one's a pretty easy to factor one. So I can write this as an x plus 3 and an x minus 1 equals 0. So my x equals a negative 3 and a 1. And again, since exponential functions have a domain of all real numbers, I don't have to worry about whether these are valid solutions. Moving on to the next one, letter C here. Before I can really do anything, I need to isolate this exponential piece. I don't know whether the bases are going to match until I get that part done. So I'm going to have a 10 to the x minus 2. Subtracting that 16 from each side, I'll get a 6. And now I can see there's no way that 10 and 6 are going to be written with the same base raised to a power. So I'm instead going to switch to my logarithmic form. Remember, you don't have to draw these little arrows. I just like to write them. It helps me kind of keep track. This base of the exponential will become the base of my log. So I'll have log base 10 of 6 equals x minus 2. And if you want to just do a quick little self-check on your handwriting, if we actually drew in a line, what we should be able to see is that everything that's sitting on the line should have about the same font size. The only thing that's truly off the line is the 10, and it's a base written as a subscript. Just a quick little note there on that. Now, solving for my x, I'm just going to move my 2 to the left-hand side. So I'll end up with 2 plus, and since it's a base 10, I can drop it. I can just say log 6 equals x. Now, this is what we would call the exact answer. We can type this in our calculator and get a decimal approximation, and we would get approximately 2.778, and that would be the approximate answer. All depends on the directions and what they're asking for. Now, remember, when you type this in your calculator knows how to do this base 10, so you can type it in exactly as you see. But when we get into our next problem, it's going to be a little bit different for us. So similar issue starting off on this one. Before I can do much of anything, I need to isolate this exponential piece. So I'm going to divide by that 8. So I'll have 3 to the x minus 7 equals 5/8. No way I'm going to get those bases to match. So I'm going to switch to my logarithm. The base of the exponential will become the base of my log. So I'll have log base 3 of 5/8 equals this x minus 7. Again, doesn't hurt to do that quick little check, draw in a line there. Do things look like they're pretty much sitting on the line and about the same font size? Solving for my x, I'm going to now have 7 plus, and what I'm going to do is I know that my calculator can't handle this in this form, so I'm going to rewrite it immediately with that change of base. So I'm going to rewrite this as natural log of 5/8 divided by natural log of 3 equals x. So this would be a good exact form. It's calculator ready. Then we can type it into our calculator and we can actually get our decimal approximation of 6.572. If you're having a hard time getting those in your calculator, just make sure to ask in class and we'll talk about how to handle that in the calculator there. All right. So that takes care of what we would call our very traditional exponential problems. Our one on the bottom, we're going to have two special cases that don't generally fall into these categories. We're going to look at one of them today and one later in the chapter. So let's take a look at this problem right here. What makes this problem really a problem for us is the fact that we have these two exponential pieces and we have this constant here. So this constant causes us an issue because if it was just for the two exponential pieces, I could put one on each side and get matching bases potentially. Or if I just had one of these exponentials in the constant, I could put one on each side. If the bases don't match, I could switch to logarithm. But the fact that I have both situations going on here causes the issue. So what I'm going to do here is I'm first going to recognize that the 4 can be written as a base of 2. So I'm going to rewrite that piece right now and say 2 to the 2x minus 2x, 2 to the x, minus 12 equals 0. And then I'm going to think about my exponent rules going backwards. I see that these two are being multiplied together, so I'm going to actually separate them. So I'm going to write this as a 2 to the x, quantity squared, minus 2 to the x minus 12 equals 0. And then what I'm going to do is this piece right here, the fact that I have this 2 to the x and 2 to the x, I'm going to define a variable. So I'm going to say let y equal 2 to the x. And I'm going to do a little substitution. Rewrite this problem then. So I'll have y squared minus my y minus my 12. So you can see where I did that substitution there. Now, what I can see here is that this is just going to simply factor for me. So I can say y minus 4 and y plus 3 certainly gets me that. And that tells me then that y equals 4 and y equals a negative 3. Of course, our problem didn't start with a y. Our problem started with an x. So we're going to back substitute now. So y was actually equal to 2 to the x. So 2 to the x equals 4. And 2 to the x equals a negative 3. Now, on this first one, 2 to the x equals 4, I, of course, can rewrite this. I've got 2 to the x equals 2 squared. So clearly, x equals 2. That one's good. On this next one, I certainly can't get those bases to match, so I can try to switch to a logarithm here. And if I switch to my logarithm, I'm going to have log base 2 of a negative 3 equals an x. And this, of course, jumps out to us because we're not allowed to take the log of a negative number. So this is considered an extraneous solution, and we just have the one solution of 2. So that's one of our special cases of an exponential problem equation, and we'll look at one more later in the chapter.